Hello and welcome to this online CPD presentation on corrosion protection. My name is Roger Hudson. I am a corrosion protection consultant with the Steel Protection Consultancy. Over the next 50 minutes or so I shall cover how corrosion occurs in the context of structural steel, discuss the factors that can affect corrosion and describe the various methods available to provide durable corrosion protection. The content will include the design of the structure, surface preparation methods, protective coatings, paint and metal types, the importance of a good specification and inspection and quality control procedures. Steel has a natural tendency to corrode in a wide range of environments. Corrosion is a natural phenomenon which in the case of steel is to return to its original oxide state. The term corrosion is derived from the Latin word corrodere, which means to gnaw or be eaten away. Corrosion, however, can be controlled using modern durable surface treatment methods. A basic understanding of corrosion helps to appreciate the effectiveness of the various protection methods that are available. Corrosion is essentially a multi-stage electrochemical process when steel, water and oxygen are present simultaneously. At the steel surface, initial attack occurs at anodic areas where positively charged ferrous ions go into solution. At the same time, negatively charged electrons are released from the anodic site and move through the steel to adjacent cathodic sites where they combine with the oxygen and water present in the atmosphere to produce hydroxyl ions. Together with the ferrous ions, hydroxyl ions combine to form ferrous hydroxide, which in itself further oxidizes to produce hydrated ferric oxide, which is more commonly known as red rust. As new reactive sites are formed, giving a more uniform surface appearance, this is referred to as general corrosion. It is known that in the absence of either water or oxygen, corrosion will not occur. Furthermore, the rate of corrosion is determined by the presence of atmospheric contaminants such as sulfates and chlorides. In external or wet environments, the design of a structure can affect the durability of any protective coating applied to it. Detailing is important to ensure that the protective treatment can be applied to all surfaces to avoid the creation of water and dirt traps that would create accelerated corrosion, and furthermore enable future inspections to be carried out without obstruction. Guidance for the prevention of corrosion by good design detailing can be found in BSEN ISO 12944 Part 3. Some illustrated examples for building structures to avoid water retention and crevices are shown in the figure here. Additionally, there are some examples for bridge structures where stiffeners, bracings and bolter connections should be considered, are shown in this figure. Surface preparation of the steelwork is the essential first stage treatment of a steel substrate before the application of any coating, and is generally accepted as being the most important factor affecting the total success of a corrosion protection system. The performance of a coating is significantly influenced by its ability to adhere properly to the substrate material. For new steelwork, the surface will comprise mainly residual mill scale and possibly some light rusting. This is an unsatisfactory base to apply modern high-performance protective coatings and therefore is normally removed by abrasive blast cleaning. Other surface contaminants on rolled steel such as oil or grease are also undesirable and must be removed before the blast cleaning process. The amount of rust on new steel depends upon the length of time it has been exposed to damp or wet environments. 4 categories of rust grades are described in BSEN ISO 8501-1 rust grade sections. The grades are illustrated in the standard and described as Grade A, steel surface largely covered with adhering mill scale but little if any rust. Grade B, steel surface which has begun to rust and from which mill scale has begun to flake. Grade C, steel surface on which the mill scale has rusted away or from which it can be generally scraped but with slight pitting under normal vision. Grade D, steel surface on which mill scale has rusted away and on which general pitting is visible under normal vision. The initial surface of new steel normally complies with either rust grades A or B. Material that is pitted, therefore rust grades C and D, should be avoided if possible, since it is difficult to clean all the corrosion products from the pits during surface preparation. For existing steelwork, as well as rust, there may be old coatings and contaminants that would also have to be removed. Methods for removal of old coatings and rust can be hand or power tools. These methods, such as wire brushing, grinding, needle gunning, can be up to 50% effective in removing rust, etc. These methods are commonly used on existing steelwork constructions rather than new. The standard for these methods is BSEN ISO 8504-3, and the standard of cleanliness is graded according to BSEN ISO 8501-1. New steelwork is often prepared using abrasive blast cleaning, either through an automatic plant or manually. Small particles of shot or grit are projected at high velocity by compressed air onto the workpiece. The effectiveness of these methods can be up to 100% in providing a thoroughly clean surface condition for subsequent coating. Existing steelwork can also be abrasive blast cleaned. The 4 standard grades of cleanliness for abrasive blast cleaning are in accordance with BSEN ISO 8501-1. These are illustrated and described as SA1 light blast cleaning, SA2 thorough blast cleaning, SA2.5 very thorough blast cleaning, and SA3 blast cleaning to visually clean steel. The cleaned surfaces should be compared with the appropriate reference photograph in the standard according to the specification. An example of steel cleaned to SA2.5 is shown. Other surface contaminants that need to be removed, mainly on existing steelwork or new steel that has been stored in external conditions, are soluble salts. Residual salts can cause failure of any applied coating by osmotic blistering, where water absorbed by the salts is retained beneath the paint film, causing corrosion of the substrate and detachment of the paint, as shown here. Several methods can be used to detect soluble salts, including the Bressler patch method and the salt contamination meter. Both methods will quantify residual salt levels, which may suggest that additional cleaning other than dry methods may be required. One method of removing soluble salts is a wet abrasive blast cleaning. The introduction of water into an abrasive blast stream contributes to the reduction of the dust hazard, particularly when removing old lead-based paints and water-soluble contaminants on existing structures. This method can produce a high visual standard of cleanliness and is effective in removing a high proportion of soluble salts. Another method is ultra-high pressure water jetting, or UHP. Ultra-high pressure water jetting over 1700 bar is gaining popularity, partly because of its ability to remove a high percentage of soluble salts from the steel surface. Because no abrasive particles are used, UHP has the advantage of not having to remove and dispose of spent abrasives. Also, at the higher pressures, lower volumes of water are used, and this makes disposal costs lower than with traditional water blasting methods. Ultra-high pressure water jetting leaves a warm surface from which traces of residual water dries quickly, but does not generate sufficient heat to cause thermal stress in the steel surface. Rust and coatings are sheared and lifted from the surface relatively easily compared with other blasting methods. Soluble salts are removed more effectively because the steel profile generally remains unchanged. This method is mainly used for maintenance painting projects. The surface preparation by ultra-high water jetting is covered by BSEN ISO 8501-4. In addition to cleanliness, surface profile is important. The type and size of abrasive used in blast cleaning have a significant effect on the profile and amplitude produced. In addition to the degree of cleanliness, surface preparation specifications should also consider roughness relative to the coating to be applied. The difference between shot and grit abrasives and the corresponding surface profiles produced is illustrated in the three-dimensional diagrams obtained from non-contact surface characterization equipment as shown here. The type of profile should be appropriate for the coating to be applied. High-build paint coatings and thermally sprayed metal coatings need a coarse, angular surface profile to provide a mechanical key. This is achieved by using grit abrasives. Shot abrasives are used for thin film paint coatings such as prefabrication primers. To check roughness, several methods have been developed to measure or assess the distance between the peaks and troughs of blast clean surfaces. These have included comparator panels, special dial gauges, replica tapes and traversing stylus equipment. Usually comparators or replica tapes are used as shown here. The relevant standards are BS EN ISO 8503-1 for comparators and BS EN ISO 8503-5 for the replica tape method. After abrasive blast cleaning, it is possible to examine for surface imperfections and surface alterations caused during fabrication processes, for example welding. Depending upon the specific requirements of the structure, it may be necessary to remove general imperfections on welds such as spatter, rough profiles and cut edges to produce an acceptable surface condition for painting. Weldments on fabricated structural steelwork represent a relatively small but important part of the structure and can produce variable surface profiles and uneven, sharp surfaces and projections that can cause premature coating failure. Depending upon the coating to be applied, joint interfaces may need to be specially treated, for example, for slip factor requirements. Fasteners should also be considered in terms of providing compatible protection with the main structure. The relevant standard is ISO 8501-3, the preparation of grades for welds, edges and other areas. Turning now to protective coatings, paint coatings are the most commonly used materials to protect structural steel. Paint is an extremely complex chemically and physically engineered material formulated to achieve specific performance criteria. Paint systems, that is, a number of paint coatings one applied over each other, for steel structures have developed over the years to comply with industrial environmental legislation and in response to demands from bridge and building owners for enhanced durability. Paints are made by mixing and blending three main components. Firstly, the binder. Binders are usually resins or oils but can be inorganic compounds such as soluble silicates. The binder is the film forming part in the paint. Secondly, pigments. Pigments are finely ground inorganic or organic powders which provide colour, opacity, film cohesion and sometimes corrosion inhibition. And thirdly, solvents. Solvents are used to dissolve the binder and facilitate application of the paint. Solvents are usually organic liquids or water, and sometimes special additives are also included into paints. Looking at the main components in combination, paints are applied to a steel surface by many methods, but in all cases produce a wet film. The thickness of the wet film can be measured before the solvent evaporates. As the solvent evaporates, film formation occurs, leaving the binder and pigment on the surface as a dry film. The thickness of the dry film can then be measured. Normally, paints are applied, usually one coat on top of another, and each coat has a specific function or purpose. The primer is there to wet the surface and adhere to the substrate, and in some cases corrosion inhibition. The intermediate coat or coats are there to build the film thickness, and the finish coat is there as a resistance barrier to the environment and also may be there for aesthetic purposes. The individual layers are measured in microns, that is 1/1000th of a millimetre. The schematic diagram shows the individual layers comprising a modern paint system. This cross-section shows the individual layers of a real modern coating system designed for long-term durability. The system is designated an epoxy type. The most common methods of classifying paints are either by their pigmentation or their binder type. This table gives a summary of the main different types of paints and their properties in terms of water permeability, cost, and surface preparation requirements. Primers for steel are usually classified according to the main corrosion inhibitive pigments used in their formulation, for example zinc phosphate primers and metallic zinc primers. Each of these inhibitive pigments can be incorporated into a range of binder resins, giving for example zinc phosphate alkyd primers, zinc phosphate epoxy primers, etc. Intermediate and finish coats are usually classified according to their binders, for example epoxies, vinyls and urethanes. The method of application and the conditions under which paints are applied have a significant effect on the quality and durability of the coating. Standard methods used to apply paints to structural steelwork include brush, roller, conventional air spray and airless spraying. Airless spraying has become the most commonly used method of applying paint coatings to structural steelwork, usually under controlled shop conditions. Brush and roller applications are more commonly used for site application, though spraying methods are also used. Modern high-performance coatings are not tolerant of poorly prepared surfaces and have limited application conditions. Correct application has become increasingly important to achieve the maximum potential of the coating. The training of operatives has been identified as an essential stage in the process. In response to industry demands, ICATS, the Industrial Coating Applicator Training Scheme, was introduced. The scheme has been operated for several years, and ICATS registration has subsequently become a mandatory requirement for contractors working on highways agency and network rail bridges. ICATS is owned by the Institute of Corrosion and operated through Correx Limited, a wholly owned subsidiary of the Institute of Corrosion. The scheme has a mandatory basic unit, known as Industrial Coating Applicator, that comprises 6 modules: health and safety, site access, plant and equipment, surface preparation, paint types and application, and quality control. There are also 4 specialist modules: blast cleaner, paint sprayer, thermal metal sprayer, and water jetting. ICATS enables contractors to provide best value service to maximise coating performance over structure life and reduce whole life costs. Looking now at metallic coatings, there are 4 commonly used methods of applying metal coatings to steel surfaces. These are hot dip galvanizing, thermal spraying, electroplating and Sherrodizing. The latter 2 processes are not used for structural steelwork but are used for fittings, fasteners and other small items. In general, the corrosion protection afforded by metallic coatings is largely dependent upon the choice of coating metal and its thickness, and is not greatly influenced by the method of application. Hot dip galvanizing is a process that involves immersing the steel component to be coated in a bath of molten zinc. The immersed surfaces are uniformly coated with zinc alloy and zinc layers. The resulting coating is durable, tough, abrasion resistant and provides cathodic protection to small damaged areas where the steel substrate is exposed. As shown here, the process is essentially a multi-stage operation. Firstly, the steel is degreased in an alkaline or acid degreasing solution. Then there is a cold rinse followed by chemical cleaning in hydrochloric acid to remove rust and milscale. A second rinse is followed by dipping in a hot flux solution. This removes any last traces of oxide and allows the molten zinc to wet the steel surface. Immediately after fluxing, the steel is immersed in a molten high purity zinc bath at about 450 degrees C before being withdrawn, when the zinc starts to solidify and usually assumes a crystalline metallic luster, often referred to as spangling. The thickness of the galvanized coating is influenced by various factors, including the size and thickness of the workpiece, the steel surface preparation and the chemical composition of the steel. In this picture we can see steel beams being withdrawn from a galvanizing bath. The product specification is BSEN ISO 1461. The required minimum average coating thickness for structural steelwork 6 mm thick or greater is 85 microns. Thick steel parts and steels which have been abrasive blast cleaned tend to produce relatively thick coatings. Here we can see a microsection through a typical galvanized coating showing the different compositional alloy layers which are metallurgically bonded to the steel substrate. There is a gradual transition from an iron-rich layer next to the steel to a zinc-rich outer layer. Applications are wide-ranging, from complex design structures to simple small footbridges, as shown here. A second method of metal coating is thermal spraying. Thermally sprayed coatings of zinc or aluminium provide long-term corrosion protection to steel structures exposed to aggressive environments. They are an important component of coating systems that are currently specified by Network Rail. For bridge components, thermally sprayed aluminium is usually preferred and it acts as a barrier coating. However, for rail bridges likely to be subjected to collision damage, zinc is often preferred due to its sacrificial nature. The coating metal in powder or wire form is fed through a special spray gun containing a heat source, which can be either an oxygas flame or an electric arc. This is the gas process. Molten globules of the metal are blown by a compressed air jet onto previously grit-blasted clean steel surfaces. The electric arc process produces a similar coating to that deposited by the gas process, except that the heat source is generated by the arcing of two electrically charged electrodes. Typically specified coating thicknesses vary between 100 and 200 microns for aluminium and 100 and 150 microns for zinc. The protection of structural steelwork against atmospheric corrosion by thermal sprayed aluminium or zinc coatings is covered in ISO 2063. Thermally sprayed metal coatings can be applied in the factory or at site. No drying time is required, they do not sag or run, and they can be applied to the required thickness in a single operation. There is no limitation on the size of the workpiece that can be coated, and since the steel surface remains cool, there are no distortion problems. Guidance on the design of articles to be thermally sprayed can be found in BSEN ISO 14713-1. The adhesion of sprayed metal coatings to steel surfaces is considered to be essentially mechanical in nature. It is essential to apply the coating to a clean, roughened surface, and blast cleaning with coarse grit abrasive is normally specified. No alloying occurs and the coating consists of overlapping platelets of metal and is porous. The pores are subsequently sealed by applying a thin organic coating which penetrates into the surface. Sealers may be either unpigmented or with colouring agent or aluminium flake. After considering the surface treatment methods, these need to be included in a specification. The overall success of a protective coating scheme can be influenced by many factors and start with a well-prepared specification. The specification is an essential document that is intended to provide clear and precise instructions to the contractor on what is to be done and how it is to be done. It should be drafted by someone with appropriate technical expertise, and it should be clear as to what is required and what is practical and achievable. Specifications may be either performance-based or prescriptive-based. Performance-based types allow the specifier to choose those treatments that will achieve a desired life to first maintenance, while the prescriptive types set out detailed requirements and include specific processes and coatings. The main purposes of the specification should define the durability to be provided, also define the requirements for appearance, provide a basis for pricing and tendering, and provide a reference document for contractors and inspectors. The main requirements, therefore, should include surface preparation and the standard required, the maximum interval between surface preparation and subsequent priming, the types of paint or metallic coatings that are to be used, supported by relevant standards, the methods of application to be used, the number of coats to be applied and the interval between coats, the wet and dry film thicknesses for each coat, where each coat is to be applied, in the factory or on site, and the application conditions that are required in terms of temperature and humidity, etc. Details for treatment of welds, connections, and so on. Rectification procedures should also be included for any damage that might be incurred. The scope of the specification will consider the structure in terms of whether it's a building, a bridge, or other type. The environment, which should be classified, the access, whether it is easy or difficult, all of the surface treatments, their preparation methods and coatings, the application methods, whether they're spraying or dipping processes, handling and transportation methods, and inspection and quality control. The environment should be classified in accordance with the standard EN ISO 12944 Part 2. This standard details a range of environments that can be encountered in interior or exterior conditions, and some examples are given here. A Type C1 category is a very low risk environment, whereas a C5 category is very high, and the type of protection required will be different for the different types of environments. Looking at surface preparation, as described previously, the preparation will be key to the success of any coating applied to the substrate. It is important to ensure that all contaminants are identified and with a suitable method of removal. The standard of cleanliness should also be quoted, for example SA 2.5. The profile, whether it be coarse, angular, and a method of measurement, whether it be by comparators or replica tapes, should be included with the relevant standard. Provision should be made for the treatment of any surface irregularities, including weldments and cut edges, and finally, the surface condition immediately before coating is applied. Looking at paint systems, in a multi-coat paint system, it's important to make sure that each coating is compatible and to source the materials from the same manufacturer. It should be decided whether there should be a need for stripe coating on vulnerable surfaces, e.g. edges, where coating can be thin, and not to forget about the final appearance. The specification also needs to consider requirements for good handling and transportation methods to minimise any damage at all stages. The illustration shows coated bridge beams being carefully lifted into place on site by nylon strops. To assist specifiers, there are model or standard systems that can be considered for a particular project. This table is for building steelwork in an exterior C3 category medium risk type environment. Others are available for different access situations and environmental categories. There are a total of 8 standard systems for buildings. Similarly, prescriptive specifications for bridges are documented with the Highways Agency and Network Rail. This example is a summary table of the Highways Agency Series 1900 for bridges and similar structures. This table is a summary table for network rail systems contained in the document NR/L3/GN039 issue 5. Looking at specifications in summary, there are many things to take into account when preparing a specification to encompass all that is required. The life to first maintenance of a new structure should consider access for equipment and a workforce. The exposure conditions may be influenced by other materials, for example cladding, which in turn will determine whether metal, paint or a combination of the two can provide the required durability. There are known performance data for a wide range of protective coatings to help the specifier. Also, the protection of other steel surfaces, including fasteners and decking, etc., should be considered at the same time as for the principal structural members. Such components may require additional coating to achieve this. It should also be recognised that some of the surface treatments may be part factory and part site applied. Site stored coated steelwork may well need to be cleaned before finish coats are applied to avoid adhesion problems. Should coated surfaces be damaged, a method of repair should be stated to avoid a localised premature failure. Finally, whilst durability may be a prime requirement, the aesthetic appearance should not be overlooked. For existing structures, when first maintenance is identified, both the condition of the protective treatment in terms of the extent of coating breakdown and a quantification of metal loss are necessary to determine a maintenance strategy. To summarise, if the specification is exacting in its requirements and quotes current standards, there is less opportunity for poor quality work and inadequate performance. Turning now to inspection and quality control. Inspection should be an integral part of the protection process to ensure that the work is being done correctly to avoid expensive remedial costs and confrontational issues. To get the best out of inspection, it should be employed throughout the contract and be carried out by a properly trained and certificated coating inspector. For example, the Institute of Corrosion scheme. Things that need to be checked. As a minimum requirement, the factors that have the greatest influence on the success of the protective treatment should be included. These are surface preparation, which starts with the removal of grease or oil contaminants, followed by cleanliness and profile, taking into account wells, cut edges and holes, etc. Then there are the coatings, whether they be metal or paints, their application and adhesion to the substrate. And modern two-part paint coatings such as epoxies to check on full curing. So who provides the inspection? Those responsible and the level of inspection should be identified at the start of the contract and their role clearly defined. A plan for inspection will determine the relevant qualification and equipment needed for the exercise. A comprehensive set of records will help to resolve any issues that may arise. This picture shows a full range of inspection and testing equipment available for every aspect of the job. This includes atmospheric condition testing, surface preparation cleanliness standards, contamination checks, profile measuring, paint film thickness measurements, and testing for adhesion and curing of paint coatings, and much more. These two pictures show the checking of wet and dry paint film thicknesses. The coating applicator will check wet films for adequate coverage, while an inspector would check the cured films to ensure that they meet the requirements of the specification. Hopefully this presentation has provided an insight into the essential aspects of corrosion protection for steel structures. The corrosion mechanism explains how steel deteriorates superficially in certain environments and the factors that influence the rate of attack. Protection starts at the design stage with the incorporation of good detailing to avoid water and dirt traps. High standards of surface preparation are key to the successful performance of any subsequently applied protective coating. The durability of modern metal and paint coatings are well established and provide a basis for material selection to achieve the required life to first maintenance. Every part of the process should be contained in a comprehensive specification to enable those concerned to be clear as to what is required and when and who is responsible. Finally, the finished job will only be as good as the standard of workmanship from those employed. Appropriately trained and certificated operatives using reputable materials along with proper coating inspection will reduce the opportunity for premature failure and costly remedial works. That concludes the presentation. Thank you for listening, and I hope that it's been informative.